All right. Well, welcome everybody back. Sunday, September 17th. This is the evening session of technical topic for the week. This topic is specific to artificial intelligence. So I'm just gonna dive right in here by quickly reminding you at a high level, again, the hypothesis that Rob and I have around generative landscapes is to achieve higher performing objectives, balancing competing interests, and delighting occupants of the landscape that we are in question with, and doing it with these co-authored three core technologies. So again, I'm not going to go through it all, but real-time rendering, parametric and performance modeling, and artificial intelligence. This session is focusing on artificial intelligence. So very quickly, I'm going to go over AI at a crash level, very fast overview, general history, future as it relates to design. And then we'll talk about the three types that we are hoping you will experiment with in this class. The first being large language models. The second is genetic algorithms. And finally is latent diffusion. And I'll talk about all these different acronyms as we go. Generally speaking, AI and computation in general, I just want to preface this by saying this statement was made in 2018 by Peter Diamandis, an XPRIZE Foundation winner, who made a claim that AI collaboration will skyrocket across all professions with AI as a service. This is 2018. It's now 2023. We are very much living this reality where AI as a service, either through genetic algorithms, latent diffusion, or large language models, we are seeing this now, and it is going to become even further entrenched as we go. The reason for making that statement is just that, look, the sooner you get on board with some of these tools, the sooner you get to design and figure out what design with artificial intelligence looks like. And I point to this author, Stanislaw Chailu, a recent PhD grad from Harvard, and was working shortly for Autodesk Research in our former SpaceMaker, now Forma division. Researcher, what he came up with. This book is really great, very much recommended, just as general background. Where does AI come from? How is it fitting into design? He has great perspective on this. Most importantly, is probably some of his diagrams that basically illustrate a timeline from 1930 to approximately 2030, and why we're seeing AI appear now. I'd be happy to dive a little bit deeper into this. I have a really strong interest in times and how technology evolves. But if you want a nice compressed and published version, Stanislaw Chailu's book goes into great detail on this. The first thing I want to mention very much up front, I'm sure many of you already know this, but there are two fundamental types of artificial intelligence that it can be applied to. There is what's called generalized AI, which is, basically AI can do everything. It will essentially replicate human behavior and have agency to do so. So this is the idea that robots can emulate everything and may take over the world. But there is applied AI. This is things to do very super specific tasks. Usually it's something repetitive, that you want the computer to do in a semi-automated, semi-intelligent way, such as recognizing things, or perhaps recognizing things and then categorizing them, such as the example here on the right from MIT's, the first AI-powered melanoma detection system. And so when we are talking about AI, we are mostly, no, we are always talking about applied AI, not even mostly. All examples of AI that we are talking about have super specific applications in mind. And apply AI examples do really specific and sometimes dumb things, such as character recognition. This is from a symposium that I helped run in 2019 with the Living Architecture Systems group, basically introducing a few speakers from Taubman, Michigan College, that were starting to experiment with this for image making at the time. And here, all I'm showing is just that there are things like data that's input here on the left, and on the right, the ability to distinguish characters, even in rough drawn format, by a system that recognizes it. Some examples of applied AI in design. This is an example of a company that's super innovative. They were one of our Autodesk Technology Center residents. Basically, by learning from lots of different vehicles, scanning them, and then being able to design with them by essentially blending different typologies together from that. So it's being able to essentially recognize a library of different designs and then help you by mixing and matching them as you go. Another example, in this case, automotive, another resident of the Autodesk Technology Centers, this company called Pixmoving, pretty interesting group that uses a combination of multi-objective optimization for the platform of their vehicles, as well as some optimization for some structural components. Just to give you a little taste test of how people are using it in the real world. But I do want to start by giving you some of the broadest umbrella picture that I can here. And for those of you that are just starting to get familiar with AI, I super recommend watching Andrew Ng, formerly from Google Brain's research division. He has a free online course. I think it's on LinkedIn. I think it's on a few other platforms called AI for Everyone. And the following diagrams that I'm giving you here are basically interpretations of part of his course that helped me remember what part of AI we might be actually dealing with, because it is a huge field. Essentially, artificial intelligence starts as a special branch of computer science dealing with simulating some degree of intelligent behavior in computers. It starts with characters like Alan Turing, simulating decision-making. A sub-branch of AI is machine learning. So this is basically the ability for a computer to learn without explicitly being programmed to do something. And so this is pioneered by Arthur Samuel, recognizing, for example, when you are always putting in for some sort of an online thing to pick a cat, you're basically helping to train data that a machine learning algorithm will leverage later. So recognize a cat in a structured photo collection is an example of machine learning. Deep learning is a subset of machine learning. This leverages an innovation in what's called artificial neural networks. And artificial neural networks behave like the way that a human brain does, where, as the name implies, in this case, a series of artificial neurons, little connectors, are making associations between things. And so it's simulating in some way the way that a human brain might work. But what it practically does is that it helps you account for multiple inputs and map an output. And this was quoted by Andrew Ng in 2016. So an example, and if you follow Andrew Ng's course, you'll see this, that you can determine the price of a house based on 4 data points. So it could be neighborhood, it could be age, it could be construction style, etc. And based on a number of parameters, it might give you a determination of a price of a house. Cross-secting all of these is a division of research called data science. And this is becoming extremely valuable because it's basically able to cut through and know a little bit about all these and know a lot about the data that you are working with in order to suggest methods that actual AI technology could actually work with. So often, people who are data scientists are either drivers of the new technology today, or they are expert consultants. Now, the flavors of AI that we're going to deal with in this course, again, that was latent diffusion for image making, genetic algorithms, in this case highlighted here for optimization, fall into different categories. And genetic algorithms fall into the more generic umbrella of AI. And that is that it's an algorithm that will receive some input, learn from what is working or not working relative to a objective you're trying to map, and then help you make a decision for higher performing options. And then when we talk about image making, latent diffusion, and even large language models like ChatGPT, I'm using the terminology a little loosely here, forgive me, but it's all deep learning. Both of these subflavors come from deep learning. So they both leverage artificial neural networks to make associations, and then they're just relying on different data pools to make what it is that they're doing. So how are some people using this techniques in architecture, engineering, and construction? So here we're seeing a company called Daisy AI, a startup that is local here in Toronto and in the UK. They're using genetic algorithms to optimize the joists of a wooden floor. Here's an example of deep learning. In this case, it's general adversarial networks to co-design a space. This is what it looks like, where a user is able to essentially draw some initial starting points, and the computer will help you fill in either details or a style transfer. So this was a project we did with NVIDIA for their new Santa Clara office in 2018, an experiment that was put into practice for that office. Or you could use adversarial networks to be another version of deep learning to help you automatically classify a space. This is work of Stanislaw Chilu, where it's basically creating a number of different floor plans for a house. And then based on their relative size and proximity, it's able to classify them automatically and fill in some details and style of that plan. And then perhaps on the most basic level in AEC on the construction side, the construction side here is a company that has cameras that learn how to recognize things. So in this case, there's a startup called Zeitgeist, also a Toronto startup, that's able to help for construction sites for things like safety. Where does all this AI come from? As I mentioned before, there are some pioneers, some seminal figures. They are mostly old or dead white guys. So I apologize that this field has been so dominated by one particular one particular group for as long as it has, but it is starting to change. However, acknowledging who the pioneers were is Alan Turing, who proposed the question, can machines think? And started to explore this as a sub-science of computer science. Perhaps next major figure, there's really three, is Frank Rosenblatt, who's an American psychologist. So not necessarily a computer scientist to start with, but a psychologist who tried to imagine how people learn and then how computers could learn, and proposed the idea of perceptrons, which in a very fundamental way is emulating an artificial neural network that we see in machine learning and deep learning today. The idea that a machine could make an informed decision based on unstructured data. And then finally is John Holland, who only recently passed away, who created the concept of a genetic algorithm. And so it's taking some ideas between biology and genetics and bringing that into the world of computation and computer science. So zooming back out, we are dealing with this version of AI, genetic algorithms for generative design, and deep learning for image making and for text prompting or text feedback. So let's talk about that first example in some detail. Large language models, what are some of the underlying principles? And maybe more importantly, what can you do with it in this course? So I'm not going to pretend to be an expert in large language models, but this is essentially the data pool that is trained on lots of examples of text that then later an artificial neural network will learn from and be able to predict and generate text from there. And I found that this, well, I'm just going to let this run, but you can go to these links here to get this. But this was a great explanation. I'm also having wine in the background, so don't mind me. So basically collecting lots of data. And then the way that it works is that it's trained to look for common patterns. So if I start with the word tomorrow, it might imagine morning. So I'll let you watch the rest of this, or you can go to commoncraft.com. It's really good. It describes a lot about how this works if you want to know. Now, how can we use it? For me, both in research and watching others use it in practice, a lot of people start by using it as a bit of a research assistant. So this was an example where we were trying to explain to a customer who was thinking about overall site design, how we might be able to introduce biochar onto their landscape site. And we needed a simple way to describe how biochar sequesters carbon, and then we needed to know how we can design with biochar. And so this became a starting point to have some initial conversation. And then you can always ask it for references, for articles, for journals, because it has scanned the internet for a lot of that information and probably can point you there. The key is when it starts, it may not always start assuming you want hard information. It's going to start from a conversational perspective and can then get deeper based on that discussion. Another example, things that we were just interested in general, what tree species sequester the most carbon over their lifespan? This was pretty interesting, not because we're ever going to use giant sequoias or coast redwoods, but further down the list, there was things like red maples, which are able to be designed with in a very practical manner, both in the lifespan of the tree itself and in terms of being able to design. But the part that I think is particularly quite interesting is being able to work with a large language model generator like ChatGPT to co-code or to co-ideate code for your behalf. And so here, I had a simple example of like, hey, can you help me think about coordinates with a sine wave equation? And could you please write that in Grasshopper Python? And after some trial and error of like, here's what's working and I can feed it errors, I can eventually get it so that I can just plug that exact script into a GH Python command and be able to let it to do work on my behalf. So the reason why this was useful is that it can help me or it can help you create both generators and evaluators if you need. So if there's something that you're seeing that is hard to describe or hard to find or hard to make in visual programming with Grasshopper, you could find a shortcut by just letting ChatGPT help you co-code something that might be more precise to what you're looking for. So I would encourage you all to kind of take a look at that, and I will just kind of quickly show you here what that actually looks like. So here's an example. I will go into more detail of this example of the Max Thor landscape that has this kind of radial pattern here that's quite evocative. It's a great case study. But these are all the attempts that I had asked ChatGPT to make for me. So I have a little script that's made, and then I make an observation. It's not really what I want, and I have a little verdict. It's not usable. I'm getting closer with each iteration that I make. It takes more and more attempts. There's some errors, there's some problems, until eventually I got to a version that I did like. I was able to get it to make a sine wave curve along a path in point form that then I could make a Delaunay mesh from. And so it was a really interesting process because it was like having a conversation with an expert who knew the syntax of Python, knew some syntax of Grasshopper, and could write code for me. The key component behind how to make this work is when you are describing things to ChatGPT, you need to be pretty precise with what you want to happen. And this is where building up your skills in pseudocode, like plain language, what do I want to happen, is key. Because if you cannot describe to yourself or to someone else or to ChatGPT how you might sequentially make something happen, you may have trouble yourself doing that even beyond the syntax of something like Python. So I found that using ChatGPT for these kinds of topics was extremely fascinating process. And I'd be happy to share some of these samples, which is, I have a sequence for asking ChatGPT what I think it needs to know. Like I ask it a question, what is Grasshopper 3D? It then knows that I want to talk about Grasshopper 3D. And then I tell it, explain a sine wave curve. Again, I let it know I want to talk about Grasshopper. I want to let it know I want to talk about sine wave. And then I say, hey, let's write a Python script that does what I think it wants to do. And it will start. And then I will find some elements that may not work. Here's like, hey, can you change the Python script so that it makes the points in the XZ plane, not the ground plane? And so it'll make a change. And then I'm like, can we have the ability to define parameters like amplitude and frequency, number of points? And then I just have a conversation with it. And sometimes it'll result in some errors. And sometimes it will work. Here's an example of a runtime error. I just get a feedback from Grasshopper, GH Python, and it's like, there's a problem. And it's like, oh, I think I can fix that. I think I know what the problem is. And it was fundamentally an amazing game changer, especially if you want to start making your own generators or your own evaluators. It's pretty powerful. So I'm not going to go into more details of that. I'm happy to share files. This is so cutting edge and new that people are experimenting with this every single day. So please take your hand at it and experiment with a very open mind. I'm going to pivot now to genetic algorithms, which is a much more robust topic. And this requires a little bit of preface. So that's what I'm going to do now. Asking ourselves first, why do we bother with GAs or genetic algorithms in design? What are the principles of evolution that are tied to this? How is this coming into computer science? And how do we access this potential? And we can do it with either single objective optimization or multi-objective optimization, or SOO or MOO. So for knowledge reference first, again, I'm not going to pretend to be the premier expert on all this, not only the fundamental knowledge, but also how it can be applied. This primer document, generativedesign.org, from Autodesk is like really, really good. I've helped contribute to these pages so that we can describe generative design using genetic algorithms, which is primarily meant to introduce these concepts to customers. It's really good. I would always point people back to this for reference. But ultimately, we are using genetic algorithms to optimize something. This is a great example here of simulating a bipedal animal that basically is trying to fine-tune how much it should be pressing on some of its little gears here in order to walk correctly. And you can see here that in generation 1, it has a random, sort of a random allocation of how much pressure to put on those joints. And as the generations go forward in time, the algorithm is learning what is not working and what is working, so that by the time it gets to a later generation, it will probably be functioning much better. So it's optimizing input parameters to get a desired outcome. In this case, the outcome is walking straight and consistently. In spatial design, such as architecture or landscape, what we're really talking about here is this evolution phase, the same as the previous one, just put into something spatial. More specifically, what happens is that a genetic algorithm is going to optimize inputs or parameters that are defining your generators your geometry creation. And it's going to optimize which version of these inputs makes the most sense for your objectives. So you need both of these. You need inputs. Sometimes this will be called genes, like the genes of a genetic algorithm or an evolution. And then it needs to know what your objectives are. Ultimately, it runs through thousands of options, maybe even 10,000 options, and it will learn from those and plot them on a solution space graph for then you to make a decision on. Now, to do optimization, you need 4 pieces of information. You need to generate something. Again, this is the generation side of things that we talked about, and we will continue to talk about. How are you making geometry? And then importantly, how are you analyzing and evaluating your performance measures? So what should we evolve for? And then you have an algorithm that searches the options for high performance. So the genetic algorithm really just helps you look for high performing candidates, learn from those, and then be able to evolve further and further on that in that solution space. So now we've always likened generative design to a process where traditional design, you start with a project scope, you do some research, some brainstorm, some defining of ideas, and then usually you design a solution, usually 1, maybe 2, maybe if you're lucky 3. And then you go to your review, select, and develop for further details. Where generative design, by way of genetic algorithms, comes into play is by essentially taking over the generate, evaluate phase by evolving it, where you design the environment, the parameters, and the objectives, and that helps co-design lots of options. So again, this is just another way to visualize this. When you are designing the solution, you have your project definition, some goals, and maybe you come up with 1, 2, or 3 ideas. You select it and then you detail it. But with generative design, it opens this phase up where now you can spend more time designing the definition, the geometry, the goals, and then it will iterate on your behalf. And eventually you can select options that make the most sense for you. I don't know how much I need to probably go into evolutionary underpinning here, but there's this really great link here from Bio Interactive that talks about fitness objectives and adaptation. And when I talk about designing the environment, the geometry, and your fitness objectives, it's super similar to a lot of things that happen with fitness objectives and evolution in real life. And so the example that this website gives is the Rock Pocket Mouse, which is a real case study in, as you can see here, this kind of habitat range, kind of North Mexico, Arizona. And this Rock Pocket Mouse was really great at its environment. It was optimized, if you will, for its environment because it was the same color as the desert floor. And so when a predator came into play and it noticed a mutation of a mouse that was perhaps not the desert color, it would take it away, and basically it has selected a way for it, and it would continue to evolve the brown mouse. So the environment is the desert condition. It is the mouse fur color that can be expressed on a range. And then there's a mutation that will change the color of the mouse, and it can be selected for or selected against. Now, in this condition, there was a real world volcano, and it changed the desert floor to be gray. And now in our normal process of evolution, the rock pocket mouse was like very much at risk because now the predator could pick up all of these mice and it called over its friends and it basically selected for more of the gray mouse, which now mimicked the color of the floor after the ash from the volcano fell. So in this case, the mutation was beneficial and it selected for it. These are the same principles that are underlying how the genetic algorithm is actually working. It's looking at a series of input parameters like the color of the mouse and the condition of the floor. It's introducing some mutation and it's saying, is that mutation beneficial or negative? And in the case of the mouse, it's life or death. In your case, it's just which geometry is matching your parameters more. Most of us know evolution, or we think we know evolution, comes from Charles Darwin. And I just want to highlight that this gets linked all the way back to not just 1859, but 1201, where the idea of how genes can be expressed differently can have either positive or negative effects. And very importantly, that we've been continuing and we will still continue to talk about genetics and evolution for the time coming. And so it's an 820-year span, which you can learn more from at extendedevolutionarysynthesis.com, which is a great resource for learning if you want to know more. But let's return. What are the 4 primary ingredients that you need in biology to work? You need to reproduce. The mouse needs to have babies. Those babies need to have a variation based on parameters such as color, size, bone density, et cetera, et cetera. There needs to be a fitness, survival of the fittest, or a competition value, like what is your objective? Could be survival. And then there's a selection process. Oh, the brown mouse in the black desert, not working well. These 4 steps have been emulated in computation. There's an initial population made. Variation is made according to the input parameters. You will evaluate the variation of those models, and you will see if it is doing well according to your fitness objective. And then you can go back and forward in this. You can simulate evolution in a very compressed amount of time. So when you wire up your scripts, what's happening under the hood is that essentially an initial population is made and metrics or objectives for each solution is understood. Some degree of selection and mutation and crossover of your input parameters is created, and then a new population is made, or a new generation is made. Well, maybe that was a little dense, but here's how it looks on another way, where a generation, in this case, 10 models are generated. And you would define the number of designs inside of that generation. In this case, you could choose 10. It will then evaluate how each of these 10 is working. And it will say, you know what? Based on your 10, these 2 here are performing really well, and we're going to learn from them in our second generation. So these variables are put on the highest regard. So if the slider said, the circle needed to be yay big, great. And it will continue to do this until you reach your final generation that you decide on, and it will probably be creating the highest performing options. So this is what it looks like when we use a multi-objective optimizer. We'll talk about that later. But I just wanted to say, hey, like this principles of genetics and evolution relative to computation is coming out now for a while, and there's lots of different algorithms that could be used. We will primarily be using an algorithm called NSGA, which only came out in the year 2000, the NSGA2. This is the one that we will mostly use. I'm not going to bother talking about these specific ones, other than to say there's a difference in these algorithms. Some of them are really good at single objectives, like I want to optimize for one thing, versus I want to try to balance for a couple of things. And so the difference here is fairly straightforward. A single objective optimizing algorithm is great at doing one thing. And multi-objective can do multiple things and usually very good at conflicting objectives. So I don't think I need to go into too much detail for this, but a designer will usually employ a single objective when you need to consider just one element. And it's more common to use multi-objective optimization because we often have many goals that we need to consider, or many objectives. So typically, this single objective optimizer gets a yellow check mark for designers, and NSGA2, the multi-objective, this is the one we will primarily tend to work towards. And again, the genetic algorithm comes from John Holland, emulating how genetics and evolution works. I'm not going to go through all the details as to how that happened, but just know that it has happened. And if you want to learn more, Kenneth DeYoung's Evolutionary Computation book in the 90s was fantastic. I've read just like the intro and a couple pages. It's pretty awesome. Now, single objective optimization, we've had one goal, maybe two goals since 2013. That's the first time genetic algorithms have been brought into a Rhino and Grasshopper and CAD environment, period. So you could optimize for views, or you could optimize for solar radiation. That's pretty common. And we can do that with Galapagos for Grasshopper. And we're going to try this in a second. But in today's time, it's not good enough to optimize for just one goal. And multi-objective optimization can consider up to and around about 8 competing goals without needing to change the underlying algorithm itself. So here's an example of a project I was working on that was trying to balance essentially 9 goals. It was really at the upper limit of what a genetic algorithm could do feasibly without starting to break down. So you can think of optimization. Again, optimizing is just trying to find the best version of something in a single objective mode. And in multi-objective, it's trying to help you balance competing goals, like Lady Justice here, just trying to imagine what are the 2 goals, how is it scoring, and it's using its artificial intelligence brain through an algorithm to help you find those in a solution space. The key thing is that you need to make sure your goals or your objectives are things that the AI brain can understand. In other words, it needs to be numeric. It has to know if something is bigger or smaller or within a range that's suitable. I don't know how this slide got in here. I apologize. But basically, it's the solution space that we're talking about here. So here's just a little GIF that's showing you the generations over time and how slowly those generations are going from random, the red dots, to something more performance-based that is repeatable through the blue and the greens. And it's finding that zone that is the best for two goals to compete against. So, okay, enough of a primer of theory. Let's start working with this. Let's start with something simple, single objective optimization. And we're going to do that with Grasshopper and Galapagos. If you want to learn more about the theory behind this, I suggest looking at I Eat Bugs for Breakfast. It is the blog from David Rutten, who authored Grasshopper and Galapagos. And he has this amazing way of describing how you could use evolutionary principles for problem solving inside of Grasshopper and Rhino. All you need to know is that there is a component called Galapagos, which takes two things, a genome and a fitness objective. Essentially, the genome is the input parameters for your geometry generator, and it needs something that's going to measure a goal or an objective that will serve as a fitness objective. So let's go through this super simple example just to get things going here. So here I have found my Galapagos component. It can be found under parameters on utilities under Galapagos. This is what it looks like. It's a special pink component. It's one of the only ones that's special colored because it hijacks your script to do something repetitive. In this case, it says, like before, you can tell the difference here. It doesn't have any output. It has a torn off graphic representation of its component. And it says, give me a genome and give me a fitness objective, and I will find for you the best. So let's try this. I wanted to do a simple generator of a circle that can change in its radius. So again, here I've just selected it, and I'll just make this a little easier here to visualize, where I basically have my radius, my center point is at 0, 0, and I'm just making a circle. That's all I'm doing. Now I want to measure the diameter of this, the area of this circle. So for that, there's a very handy component called area, which says, give me a geometry, and I will find for you the area and the centroid of that geometry. So I'm going to plug this into here. And because my file is set up in meters, it's measuring area in square meters. So as my radius changes, the residual area will also change. No rocket science here. The bigger it gets, the more area it has. So now I know the answer to this question, which is what a radius will give me the biggest, what radius will give me the biggest area. But I want the computer to figure it out as well. So to make this work, I'm going to take the genome plugin or the genome node, and you'll see here it has a red line and it has a little genetic algorithm twisty helix as its icon. It says, you give me the inputs, and I'm going to point it to the radius. So again, this is my input value, my genomes, the parameters of my geometry system. And my fitness objective, it's green here. It's like, what is the number you want me to consider? And I'm going to take this number value. So all I did here was have my area, and I have a number parameter, a container of data, and I'm going to feed that here, and I'm going to flatten it always, just in case there's lists of data. I only wanted to consider one value. And then all I did here was add it to a panel, which tells me how many square meters I'm actually dealing with. So I'm just going to get rid of these because it's repeated here. And now I have a genome and a fitness objective. And I can double click on this particular, I'm just going to move my screen over here so I can see this editor. And the Galapagos editor, you'll notice it has whited out all of Grasshopper in the background because this is going to hijack the way that it works. And it says, it gives you a little link here, the blog posts on I Eat Bugs for Breakfast if you want to learn more about things. But it gives you some options here. It says, do you want to minimize me or do you want to maximize me? And for this little example, I wanted to maximize things. And I wanted to use a runtime limit. You can say, do you want it to go for a time limit or not? I'm not going to bother. And for my solvers, we're going to use an evolutionary solver because that's what we've just described. There is another solver called annealing. We're not touching that today. We're not touching that probably at all. You're going to stay with this little, looks like sperms attacking an egg. It's the genetic evolutionary solver. That's the one we want. And it's going to record the species here just as a record. So we can hit Start Solver. And what it's doing in the background, you can see here it's changing my inputs. It's hijacking Grasshopper. And it's learning from the outputs. It has made an initial population. And it's starting here, this little graphic display is that it's showing you, hey, here's all the generations from left to right, generation 0 to generation 28, 29, 30, and it's creating a series of outputs. These values here on the right are essentially the values of the square footage of that value. So 7,850 square meters. It looks like it has either stopped or frozen, both of which would suck. I'm gonna try to stop the solver in the background here. 1 second. So unfortunately, it has frozen my computer. I'm just going to pause. Oh, maybe it's back. It looks like it's back. Maybe because I clicked on it midway. Apologies for that. It's paused now. Not to worry. But what I can display here is, instead of showing me all the evolutions, I just want to show the highest performing options. And here is this version that has 7,853 square meters. And I'm like, that's a value I want. And I can click on this button called Reinstate the Genome into Grasshopper. And you can see now it has pushed this radius value of 50, no surprise, the biggest one that I could go with, to create for me this fitness objective. And so all that's doing is this. Now, if I wanted a different, I'm like, you know what? I like the way that this version looks, a smaller version, and it's getting me close to my maximized value. I can reinstate that value into Grasshopper. And you can see it created a little subtle shift between these two, 1 and 2, just the difference between what that fitness objective is. Okay, once I'm done, I can hit OK, and it has basically ran that study for me. and I've reinstated the genome. It has told me which slider value produces the best fitness objective. Now, this is a super, super simple example, one that arguably we as humans would already intuitively know the answer for. And so single objective optimization is a little tricky because most of the time we may know what the solution could be. Things get a little more interesting when it becomes more complex. Here's another example. This is one that I've been working on in Autodesk Research. Slightly different. It's not the same. I've transferred stuff over from Dynamo to Grasshopper. But what is interesting here, this is an example that we're working on a lot, actually, is being able to use attractor points to create a series of sine wave deformers onto a topography. So in this case, it is moving a series of points around. Forgive me, it's representing these dots in a weird way. Let me just turn some things off. There we go. What I actually want to happen is to visualize these dots this way. So when I move their X and Y coordinates around, you're just seeing it as that little black dot. So you're welcome to follow along in this example here. It's basically going to be found inside of your technical folder under Surface in the FTP, under Autodesk Research Surface Generation Functions. And I'm using this Rhino file, functions.3dm, with this Grasshopper file, Surface Generator Functions 01A, if you want to follow along. And what I'm going to do here in the background is I've already strung up a slightly more complex generator, but my evaluator is the same. I'm just going to evaluate area, again, in square meters, the total area of this surface. And I want Galapagos to find for me what is the best position. Let me just make sure we got this straight. It's taking in 4 genome components to start with, the X and the Y position of generator dot number 1 and generator dot number 2. And it's taking in the sine wave frequency and sine wave amplitude. And I want to maximize the area that comes out of this. So again, I'm just going to do a maximize. I wanted to use a genetic solver, and I want it to start. So it has a weird pause at the beginning because it's observing all the parameters, and it's going to build an initial generation 0 for you. And you can see it's doing that because it's hijacking Grasshopper. Here it is learning and starting to get some initial values. So here it is starting to create generation 0, generation 1, 2, 3. Notice as this diagram starts to taper in the y-axis, it is effectively finding better performing results. And so generally speaking, if your Grasshopper file by Galapagos is getting tapered more, it means that it's probably going to find something that is working. So here it is in the background, visualizing some results. I wanted to display everything. There are ways of visualizing this a little differently. The slow version here is to, the fast version that takes up the least amount of computation visualizes every 10th version. The one in the middle here visualizes every maybe 5. And this one here on the right would show you literally every single iteration that's being made, but it goes super slow. So just be mindful of that. And there's different ways to read these graphs. And again, you can go to your options here and you can read any of these links. They will take you to a website which tells you how it's working. But I can already see here that my solver is starting to taper off. It's starting to not find better versions by generation, 19 here. So I think what I'm going to do is I'm going to stop the solver here at generation 20. And I want it to only show me the top 10 genomes that are making the most amount of surface area. And it sees here that it ranks it in this way. So I am looking at this 3,226 square meters, and I think it's good. So I'm going to reinstate the genome there versus here. And you can see the difference that it makes when I reinstate these different genomes, the impact it has. And yeah, this is the version that created the most surface area, taking into account position of these attractors, the amplitude, and the sine wave. It has found for me the highest ranking results that I could get of 3,226 square meters. So there's a slightly more complex version, but we'll talk about how you can find goals that will compete and conflict and ones that are naturally in tension, because those are the really interesting ones to have a genetic algorithm solve for you. But let's go on to our third topic of the day, which is artificial neural networks with latent diffusion. So we're going to talk about how does diffusion work, what are the tools you can use, and there are now, in my opinion, two different categories of tools. There's ones that help you ideate something new, and ones that just help you visualize things. So let's talk about latent diffusion definition and origins. If you haven't watched Last Week Tonight with John Oliver on AI images, I super recommend watching it. It's great. It's hilarious. He talks about some principles. It's a really fun way to start learning. But many of you kind of experience latent diffusion, which enables text to image creation. You put in a little prompt and it starts to make a series of examples for you. How does it do it? John Oliver gives you a general description. This is the description he gives, which is you have some inputs, it's training an AI from a library, and it gets you an output. Great, but it's actually three pieces of technology coming together. The first is automatic labeling and cataloging of components and features in images. The second is a natural language search or a call-up. And finally is diffusion or Gaussian blur techniques to randomize and combine pixels to make something new. Now, we know all of these three technologies. They're not brand new to us. The cataloging, as you would have probably guessed, we have helped as human beings using any of the Google tools or other to help classify and catalog images for a long time. Searching, super simple. It's what you normally use in search algorithms, words that would associate things to other things. And then how to mix it together. Gaussian blur, as an example, you can use that inside of Photoshop today. And you probably have been for a variety of reasons. It just mixes things together. But these three pieces of technology took a while to get here. So automated image captioning happened around 2015. TELUS International Research really was doing a lot of the bulk work of asking, can I use an algorithm to help me label and catalog parts of images or features? And then could you run it in reverse? Could you say, can I use an algorithm to help me title an image based on the features? So can it say, based on all these individual elements, can you label it as something shorthand, people walking on a bridge? And then Amazon Web Services really pushed it forward by saying, can I use an algorithm to help me use natural language call-up to create an image? So can I have the text prompt, people walking on a bridge, and it will find for me an image of people walking on a bridge? Nothing groundbreaking here, right? But it's really this text to image call up under, again, Amazon Web Services in 2017, where you could have images being created after an application of a blur. So here is test images from this paper in 2017. They look kind of crappy, I'm not going to lie. But a text here, a stop sign is flying in blue skies, it's sort of there. A herd of elephants flying in blue skies, not bad. A toilet sits in an open grass field. A person skiing on sand. We're getting pretty close here in 2017. The difference of what we're seeing today is just how sophisticated the images in the library are, the call-ups, and the degree of diffusion that's happening. Here's an example from OpenAI, the folks that make DALL-E. Here's an example of them diffusing down an example of Frank Gehry's building, and then being able to say, I want a Frank Gehry building that maybe looks like the Walt Disney Hall. And it will pick pixels from there and start to associate pixels that should be together to create something new. So the oversimplification of image input, trained AI from a library to make something new is actually a little more complex under the hood. We are now here. We started in this world of making images with adversarial training, and we have now gotten down to diffusion models. So if you want to know how things work, it's based on some of these discriminators and generators, but essentially it's using Photoshop noise to help you get there. I'm not sure if the audio is coming through here, but if you want a good description, probably a more succinct description, DALL-E and OpenAI has a great video here that describes how this is working. So I'm just going to let it run in the background here, giving you a little history, how they got there with adversarial neural network, artificial neural networks, and how it's making these images. And what are its limitations and what are its pros and cons? Great. Thanks, John Oliver. But let's talk about how we can use this in design, more specifically architecture, engineering, construction, and landscape architecture. Why would we bother using this? Because the limitation is that these images are art. It's not architecture or landscape architecture for now. It does not understand pieces coming together, like the complexity of a Gothic church, of, let's say, a spandrel being connected to an arcade arch coming down to a pier and a shaft and a base. It is making art, interpretations, images of what it thinks is good. Oh, this is a weird slide that slipped in. Don't worry. I'm just going to bullet past these. The main advantage that it's giving us today is that it can create lots of iterations. Here's a quick sample of how the foam cutter technology was helping Atelier Hans Hollein generate up to 100 models in a month. Here's an example of Zaha Hadid's office creating 1,000 options in one day. So the order of magnitude of iteration is super high. Now, how would these opportunities translate? This is a little crystal balling. From 0 to 2 years, we can help it for visualization, maybe some concepts, maybe customized models on a unique style. In the near term future, 2 to 4 years, we will see AI text to 3D models. This is getting compressed. I'll explain why. But maybe can help with things like repetitive drawings, technical drawings, maybe even some optimization. And in the next 5 years, maybe even further democratization. To borrow from Ratatouille, anyone can cook, maybe anyone can design. So how are people using this already? Well, on the conceptual side versus the commercial side, you have people like Matthias Del Campo and Andrew Cudless at different universities coming up with really interesting ways to, really conceptualize how these tools can be used. And on the commercial end, we have people like Tim Fu from Zaha Hadid, now on his own, and Jeff Powers from Thomas Heatherwick's office, using it for much more practical means. How can I make an image that I can sell to a customer or a client that then I need to reverse engineer and make? Versus on the conceptual side, how can I use latent diffusion to really change the way I think about design, period? And somewhere in the middle, you have experimental studios like Hassan Ragab, Egyptian designer, really great work, and Ant Studio, Manas Bhatia. Both of these guys kind of unknown. And it's really democratizing design to be at the power of whoever is behind the algorithm in question. Here's just a couple samples of people really pushing things. This is, again, Matsys, more on the conceptual end of things, looking at ephemeral architectural designs. The commercial side, maybe not as exciting. This Tim Fu work while he was at Zaha Hadid, much more about the kind of practical means, but still very interesting because you could imagine how some of these could be translated into a 3D model. And then somewhere in between, you get these really interesting experimental practices that are pushing boundaries that neither traditional academia or commercial are pushing things. So again, cool, but why would we do this? So there's a couple of hypotheses as to why using latent diffusion might be beneficial. One is to consider some climate issues. Maybe there's a way of recycling materials and thinking about new aesthetics that might be interesting. Or a second might be some social or human issues. Can you reimagine how a neighborhood, a park, a collection of housing might get put together that is fundamentally different? And I think it all stems from aesthetic paradigms. So I'm quite sensitive to this, and I know quite a few students want to bring a sense of aesthetics to the class, which I think is great, because I think aesthetics actually forms the basis for a lot of negative repercussions down the line over many years. And I love picking on the TD Bank in Toronto as an example. Here's an example of an aesthetic paradigm or an agenda to use glass, steel, and concrete. And it has become so popular that people want to use it everywhere. Well, the repercussion is that these types of buildings, or a landscape equivalent, would have super high embodied carbon materials, and they require high operational energy to maintain them. The social impact is that these buildings have strong sense of corporate and capital power of owners, and it feels like you're in a panopticon as an occupant of the space. You can feel lost or insignificant or watched. And so, while we have these champions of design like Mies van der Rohe who made these buildings, these are some of the downstream effects. So I think it's up to us to reimagine new aesthetic paradigms using tools like latent diffusion to reimagine what our built environment could look like. Okay, enough theory. What are the tools that we can use? Well, the first subcategory is co-ideation, and then there is co-visualization. So here you are coming up with new ideas, and here you are taking your ideas and just refining them and tweaking them, and both of them help you ideate for sure. but some of them are a little more abstract and surprising, and some of them are a little more, you kind of know what you might get. Both of them revolve around prompting, how to put in some text in order to get something else out, or at least a text-based engine that you will have to interact with at some level. So how can you start there, and what are some good principles, even as engines change? So for co-ideating, again, these are the tools that help you imagine new things. Midjourney is a great example. There are lots of tools out there. There's Crayon, Starry AI, Midjourney, DALL-E, Stability AI, and Hotpot. Hotpot's really fun. So which ones do you pick? Well, maybe top 3 so far in design communities are DALL-E, with DALL-E 2, or DALL-E 3 now is coming out soon. Came out in April 2022. Midjourney is another pretty amazing one. Actually, we're going to leverage this one the most. And then Stable Diffusion. And here I just tell you, where it's coming from, who's behind it, when it was released originally, is it for profit, is it open, closed, etc. A lot of these rely on image libraries in the background. Midjourney and Stable Diffusion both use Lion 5B. It's open and not for profit. It's called 5 because it has 5 billion data points, and is constantly being enhanced. And some of them have different focus. The algorithm is focused on more general image making. Midjourney really focuses a lot on design, space, and depth, and they keep claiming this in a lot of their new releases. And Stability is mostly around 2D graphics, but it is getting different and better over time. There's elements of censorship behind it and features and different interfaces. DALL-E works through a web interface. Midjourney works through Discord. Stable Diffusion has its own, and sometimes you can download APIs inside of tools. For all of these reasons, this is the same prompt across all 3, just for funsies. Futuristic hyper-ornamental column tree. You can see that, I don't know, in my opinion, I think Midjourney creates some of the most compelling examples. There's a sense of depth, there's balance, there's it's trying to interpret ornamental and futuristic in an interesting way, and it still looks like a column tree. These examples did not yield something that I thought was compelling. And so it's for these reasons that for co-ideation, I will predominantly focus on Midjourney. We may use DALL-E for some, outpainting or inpainting. Stable Diffusion does some interesting stuff with ControlNet, which I'll talk about in a second. But I think you'd be best positioned to start your experimentation with Midjourney. When you're starting with Midjourney, it's easy to get lost. So easy. My recommendation, this is this amazing article on Medium, which says how to understand your subject matter. And this article talks all about just using Midjourney to stylize circles. And just see, starting with a simple word, circle, and maybe adding circle with something else, you can start to see how the algorithm under the hood reacts to your prompt. When you start getting into spatial design, like architecture, urban design, or landscape, it's easy to lose track of your subject matter. And so it's important to nail down your prompts to just 1 or 2, maybe 3 words to describe what it is you want to work on. So I would encourage you, when you start with something super simple, like, is actually what you're working on for landscape an aerial view of the landscape? Maybe you want to always look down or across on it. Is the right word to use park? Or is the right word to use landscape? Or is the right words to use topography? You're going to have to test each of these words and see which one of them actually represents your subject matter that you want to work on. Now, the most powerful part about something like Midjourney or any of these generators is to mix things together. My most favorite of all music videos is the pineapple pen. Basically, you're going to mix your subject matter with something else to get something interesting. Examples here, literally taking the pineapple, what does a pineapple and a bus terminal look like? How would those two things coexist? Maybe it's helpful to think of it that way. Maybe it jogs some new ideas for you that you would have not imagined previously. That's the kind of power of these tools, to mix and match things that might not belong and see what comes out. And maybe it's inspiration for your generators. Here are some Midjourney examples, typing in circle packing, aerial landscape. And some of these, they're okay. Some of these, though, here at the bottom are pretty interesting. Maybe some circularly defined park elements could be kind of cool. And so the reason why you would use such tools is to, just jog your brain and think of something different. Here's some other ones, mixing in the word Voronoi with topography. It generated some really strange results here. But maybe some of these actually look kind of compelling. And maybe you're like, you know what? The Voronoi geometry is kind of neat. Maybe I do want to work with this. You can reference in things like drumlin fields. If you guys are not familiar with drumlin fields, these are particular patterns of hills that are basically made by the scratching of glaciers against the earth in particularly linear patterns as the glaciers retreated. And we have some pretty major high presence of drumlin fields just inside of Lake Ontario. So you could imagine some patterns for that. And I love to think about using latent diffusion technology for coming up with patterns of landform, period. And I think somebody you guys might find interesting is the work of Zanita Hong, who a few years ago had a land formation catalog at Harvard and came up with a whole bunch of really interesting descriptions of landform patterns, pseudo-parametric, that might be inspiration for you. Maybe you visualize them graphically first and see if it looks and feels interesting to establish an aesthetic baseline. And then once you have that baseline, then you can start to translate some of these into actual grasshopper patterns. It's also worth mentioning that Autodesk Research helped basically support Zanita Hong a few years ago in 2020 to investigate some building processes for landscape at our Boston Technology Center. So, you visited the Toronto Technology Center. We have another one in Boston, and Zanita Hong's research was developed and built there. So maybe that helps you co-ideate, which is great. But what if you want to just visualize some stuff instead of coming up with brand new ideas? Well, this is where ControlNet has really changed things for everybody. In the spirit of TV hosts, total game changer. What is basically happening with ControlNet as a technology? Oh my God, this image is so low res, I'm sorry. But it's basically taking a model, an image of a model here from Revit, and it's able to add some stylization to it. How does it work? It basically takes an image and it detects either edges or depth, or sometimes both. And it's able to say, hold the image here along these edges that are really a distinguishing feature. And then through a prompt, a text, change the output. So pretty amazing results. If I do say so, you're able to have an image to start with, and then you can generate all these different permutations. So in design, it could be something as simple as a drawing, even a black pen on white paper drawing that you can input as it's actually a skyscraper or perhaps a desk, and you can change its effect. And yeah, basically ControlNet, as the name suggests, it gives you more control over some of your creativity. Now, this has been mostly explored and developed under Stable Diffusion. So I would encourage you all to, maybe take a look there. But Rob basically has helped expand the possibility of some new ControlNet tools with his suggestion of LookXAI. The short form is there's lots of tools here as well. So like DALL-E and Midjourney and Stable Diffusion are great for co-ideating. Veris, LookXAI, which depends on Stable Diffusion, ArcoAI and Ambrosianus toolkits, these all allow you to do ControlNet co-visualizing on your Rhino interface. So here's an example of Veris. A tool that I was demonstrating in class on day one, where it is reading the edge of the typical model here, and it's just taking a prompt and stylizing it in a new way. Here's an example of Veris standing on top of Revit. It's reading a simple model that's Stephen Kurlas. He's got a great YouTube page. I would super recommend watching him. It's really great ideas. And it's able to create these great outputs. It works for both Revit and Rhino, and I think now there's also a SketchUp. ArcoAI, yeah, it's okay. It's a lot more expensive than I thought. I would actually not recommend it that much. But here's some examples of ArcoAI that have been really highly promoted. I'm forgetting the name of this YouTuber, but he's got some great examples. Oh, here it is, Gedan. Some really interesting results that he was getting. Luciano Ambrosini does a lot of this inside of Grasshopper for like $0, zero interface. It's right inside of Grasshopper, which is kind of fun. So you could try doing this if you wanted to. It's a little difficult to set up, but it's there. And the LookXAI is also great, very similar to Veris. It just stands on top of your Rhino viewport, and you can have a lot of control to make images. Now, what's common between both the co-ideating tools and the co-visualizing tools is prompting, entering words or phrases that drive an image. Now we're going to start with, Midjourney to understand some fundamentals. For those of you that don't already have Midjourney, you're going to go to midjourney.com, either join the beta or sign in. It needs a Discord account, so you may need to do that. I think most of you have a Discord because you're in the class Discord. If you don't, you'll need to create a Discord, accept an invite. It's just the way it works. Why does it have Discord? It's just one way people can enter text and media into real world servers. Midjourney accesses your input and basically spits material back out. So again, in our oversimplified version, the image input parameters by text is entered through Discord. It's accessing a server. I think Midjourneys are in Utah. Many servers are either in Utah or Arizona, and then it spits it back out. So I'm not going to go through all of this, but you need to authorize your account. It will pop up as a little Midjourney server, either on your web or Windows interface. The web interface looks like this. You can see your previous creations if you want, or you can do it directly through Discord. The web is a great way to see other people's work and get information and see what their prompts are. But honestly, the Discord is the main interface that you'll want to work with. You can also manage your subscription. The basic plan is good enough for what you need to do in the class. It limits what you do to 200 generations per month. I honestly don't think you'll need more than this. But if you want to go more, the standard plan is also pretty good. Yeah, I do recommend the $10 per month plan. It's $10 American, about $14 Canadian. Pretty great. You can access member galleries, borrow prompts. You get commercial terms, so you can sell your images if you want to. They charge because there's server calculation and storage fees, and there's access and rights to image libraries. These are the main reasons that you pay for it. The other reason I super recommend a paid subscription, not the free, is that you can have a direct chat with the Midjourney bot. You can read over this in your own time, but if you don't use the paid version, you get thrown into the mix with everybody else, and you'll see that you get tossed into these channels inside the server, and your versions basically just get thrown everywhere, and it's so hard to track. When you pay, you get a direct chat with the Midjourney bot. It's a private chat, and all your images just go directly where you think they're going. You can add now a Midjourney bot to other servers. So for our server, whoever is the server administrator, if you want to add that, you can do it. So people can experiment with Midjourney right inside of our course. And next is how to do prompt crafting or prompt engineering. So the next set of slides are basically colored in either green or gray or dark. So green is just tips and tricks. Observations is just general ways to work. And then gray is an example of someone else's work. So when you start with Midjourney, I recommend adjusting your settings. So you can type in /, let's go here, /settings. I'll just make this big so you can see it. So I'm doing /settings and enter. And when you do, you can pick the model. So version 5 is the one that you're forced to use now. In the past, you could use previous engines like 3, etc. You can change your stylization. You can change it from public mode. You can do remix, low variation, or high variation. And the rest of these are just how fast you want it to go. Now, Rob and I have added lots of different resources to learn from this. Basically, what you can do is go into your FTP here, and you can go to references, and you will be able to see a number of different examples of, oh, let me just go up here. Under tips and tricks, there's the Midjourney prompt guide, there's command cheat sheets, there's Midjourney 5.2 introduction and settings. There's all kinds of ways for you to learn how to change some of these settings and parameters. So that's just where to do it if you wanted to know. Now, prompting guidelines are going to change from version 3 to version 4 to version 5, and it can get kind of frustrating to know how to approach making such prompts. But I would super recommend that you just start with a couple words to see what you get. And you'll notice that Midjourney spits out 4 images to begin with. They're always in a 4 2x2. They're always arranged from 1, 2, 3, and 4, which then you have some control over changing with either upscaling or increasing their resolution or creating variations. And you can re-roll on these, or when you hit reversion, it will remix it, allowing you to change your prompt ever so slightly. So what is prompt crafting? Basically just the ways, the words, the syntax that makes your images. Prompt crafting is one aspect of image creation. It's not everything. Prompts are abundant. I do recommend that you share it with your colleagues, and that they are syntax specific and they are changed from engines to engines. So as I mentioned, there's some tips for text prompts, things to just keep in mind regardless of the engine. The case of words doesn't have any or much impact. So Christmas tree versus Christmas tree, just use lower font. Relative distance between words has a major impact. So angular space Christmas space tree, big change between these things. I would encourage you to try these out and see what you get. I made a series of Christmas cards last Christmas, and it was super fun to try all of these. And then sequence can have an impact. So whether parametric, in this case, comes first, or angular comes first, or Christmas tree, if you rearrange those, it's kind of a big deal. And then there are some obvious things. Again, this will be in the guides that Rob and I have shared. Double hyphen allows you to change a modifier or a setting to the Midjourney algorithm, like aspect ratio 3:2 will change the shape of the image. So it's just how, watch your spacing and your syntax for this. You can obviously go to settings to change it if you need to. Colons in general add weights. So a double colon with the number 1. So in this case of the Christmas cards, angular parametric only has 1. Christmas tree has 4. So tree will have more. But you can also use colons to separate ideas. Commas will also do that to a small degree. And general good working guide. Some of these are a little older because I was teaching version 3 and version 4 last year and the year prior. But generally speaking, I would say your prompts should be not that long, always to start. When you're experimenting to get down to your subject matter and your mixing agent, start simple. Start like, here's an example on the left. In the style of John Bauer, magical glowing witch hut, blah, 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 blah. Here is an example which has just much simpler description, and it gets very similar results. This one on the right, way easier to visualize, change, and ultimately control. So please definitely try to do that. The other thing that's a good working guide, version 3, version 4, it's the same way. And version 5, just work in methodical sections. Try to break it down where there's like a subject matter plus your mixing agent, and then any modifiers at the end, and maybe some final parameters that you want to deal with. Version 4 is, it can work with what's called word salad a little bit better, just mixing it all together. But for your own sake and sanity, maybe just work in a more methodical section. Chronology and sequence in version 4 and version 5 does not seem to matter too much or as much. You'll see in version 5, it's a little more sensitive. So here's imagine a red house on a green hill. And here's a green hill with a red house. So green hill came first or last. Doesn't seem to affect it too much. But chronology does. So a red house on a green hill, a green house on a red hill, very different results. And general word placement and association. If you're working towards a longer prompt, Just think that things get combined together in subsection combinations. So place relevant words closer together, unwanted combinations further apart. And again, in this case, the setting is a house. Then the first is the setting, Banff, beautiful lake, the subject matter, and then the detail. Specific words are better than general words. So contemporary architecture generates whatever the image bank is based on, but a bungalow is much more specific. So I'm encouraging you to also be specific in your words. And words carry visual tone beyond literal meaning. So Art Nouveau architecture comes with color and general framing and whether it's symmetrical or not. Here's an example of Renaissance architecture. So I'm just typing in architecture with different styles, and you can see the impact it has all the way down to color. Version 3 and version 4, major difference. Version 5 is closer to version 4. Art Nouveau architecture versus Renaissance versus Metabolist. If you want to understand what's inside of the image bank, you can go to this URL here, basically to explore what is inside of the image data bank of Lion 5B. And you can go here, and if you were to type in architecture, you'll see that there's books. A lot of them are modernist, and that's what Midjourney has learned from. So it may be better to keep experimenting with more precise words. Generally, across version 3, version 4, version 5, just keep pushing yourselves to find it's an exploration process. Find designs that resonate with you. Here's an example of starting at the bottom somewhere, and then over a series of minor refinements, you're pushing yourself until you find something perhaps quite novel. So these are just some examples of people. Here's some prompts, exploring deep, subtle tweaks until you introduce some disruptor words. This is coming directly from Tim Fu, who's kind of like an expert now in this field. And you can kind of see what's coming out here. Major Good Working Guide, learn from others. Go to the Midjourney website and start to look at other people's prompts, copy it, change it, experiment. If you want to copy other people's stuff, you can go to a specific image. You can go to copy, full command, or prompt, or job ID. I do recommend copying the full command. It's the most useful. Here are some other examples. Hassan Ragab, again, the Egyptian designer, really great. Here's some examples from version 3 to version 4. He's got some stuff in version 5. There's some image blending now inside of Midjourney. There's also some in-painting. Try different ideas, see what you get. Understand some of the basic anatomy of how a prompt is put together. And there's some reinforcing weights you can use on certain words, like there's ways of adding more words into the mix, scatter and repeat words if you really want to emphasize timbre, or add more relevant or precise words, or maybe add a relevant, this should say image, my bad, more add relevant images to get what you want. So I'm gonna stop here for now, and I'll publish this out. But I think one of the big goals for you guys to do, likely this video will be published in the morning, is to start playing with each of these elements yourself. So for large language models, maybe just start experimenting with ChatGPT to start, period. Maybe get it to help you explore what a metric could be or an evaluator. In the case of genetic algorithms, maybe you want to try Galapagos and just try to get a parametric model that you're learning from the previous video to optimize for one super simple, even if it's a dumb goal like area. Just try it yourself. get used to it. And then on the image generators, start with Midjourney to begin with. And as you're gaining more familiarity with it, we can talk about ways to expand what you're learning. But look at the references of people like Zanita Hong and a few other landscape architects that are doing this. Most of them tend to try to mix patterns and landscape typologies together to get something different. And honestly, that's an opinion I would share. You can get to some really great results that you might not have otherwise seen. So other than that, I'm going to sign off for today and let you guys digest all this material yourselves. So I'll stop now and share this video up with you shortly.